This is the second lecture in Unit 5, our unit about light and energy and periodic trends and electrons. So this one is definitely about light and energy, which applies because we're worried about the concerns with or discussing the transitions of electrons within atoms from ground state and lower energy levels to higher energy levels when they're excited. And then when they fall back to ground state, we can see those. Some of those can be seen with our visible eye, and some of those electron transitions, the energies get released that we can't see. But this is how it relates to atomic structure. Please make sure that you've completed these learning targets before you continue the video. Have a good foundation set. Some of this information will be review for you, some of it will be new, and then I'll try to touch on the important pieces as I look at the lecture. So stop the video and then go ahead and start it when you're ready. All right, here we go. So the electromagnetic spectrum, or the electromagnetic radiation spectrum, spans all the way from X-rays and gamma rays to radio waves, etc. And it's a form of energy that is wave-like behavior as it travels through space, and always all light, regardless of the wavelength, regardless of the characteristic, travels at the same speed. This is rounded here at 3 × 10⁸ meters per second. You probably put in your notes the non-rounded number, which would be 2.998. For some reason, my Apple Pencil will not connect. Let's see what happens here. 2.998 times 10⁸ meters per second. So you should memorize that number, and we'll talk about that, how you use it, etc. That number should already be in your notes. Please notice that there's a very small part of this spectrum that we can actually see with our own eyes. We can detect this electromagnetic radiation in the entire spectrum using technology and equipment, but our eyes can only see this small range of the spectrum, and this would be from 4 × 10⁻⁷, or 400 nanometers approximately, to about 700 or a little bit more nanometers. So this is the part that we can see. The rest of it is we use technology to detect. So we describe waves of energy and waves of light using two characteristics, wavelength and frequency. The wavelength is the distance from the high point to the high point of a wave, called the crest to crest, or from the low point to the low point of the wave, which would be trough to trough. So notice that those should be the same. Make sure that you're going from one high point to one high point, or one low point to one low point, not from high to low. So that would be the wavelength. This is often measured in meters, but sometimes, especially in visible light, we talk about it in nanometers, or for other parts of the spectrum, we may talk about it in centimeters, etc. So just be really careful and watch the units. Frequency is the number of waves that will go past a certain point over a certain period of time, usually per second. This unit is credited to Hertz, who worked a lot with electromagnetic radiation, but the frequency unit is an implied cycles or waves per second, but this is implied. We never use those words, so when we're calculating, we'll talk about the unit of frequency as per seconds. Strange. All right, so we use this one in our calculations, and often we use this one in our descriptions. So definitely be aware that they are equal to each other. The relationship between wavelength and frequency and energy is definitely something that you need to be aware of. Because of the characteristic of waves passing over, going all the same speed, passing past a certain point in time, longer wavelengths have fewer waves passing in the same time period. So long wavelengths give you low frequency, and short wavelengths give you high frequency. So these are inversely proportional. They're related by the speed of light, and we'll talk about that in a second, but this relationship is really important. Also, you should know that the ones with higher frequency and short wavelengths have high energy, and this makes them more dangerous to us, and long wavelengths and low frequency are definitely lower energy. So electromagnetic radiation that's lower energy has fewer effects on living things. So the speed of light is a constant that relates the two. Remember that they're inversely proportional, but they're not, you can't multiply them together to get one. So the constant that works for this is the speed of light, and you should memorize this constant at 2.998 times 10⁸ meters per second. You should also memorize this formula for our unit. and be able to calculate with it. You need to really watch the units on wavelength because often they'll be given in meters, which is great, but if you're dealing with visible light, you'll probably be given nanometers, which means that you'll have to convert to meters. So remember that 1 meter is 1 times 10 to the 9th nanometers, and pay really close attention to the units. Also remember that when you're calculating, you'll use frequency in per seconds. We'll do some calculations in a minute. The second formula that you'll need to know will be the one that relates energy to frequency, or we can rewrite this using energy and the speed of light. So we'll do that in just a second. This would be the energy of a single photon of light. So remember that a photon, according to Einstein, is a little packet of light energy, the smallest amount of light that we could have present. So this is kind of part of his photoelectric effect, was part of that creation of that vocabulary. The relationship between energy and frequency is direct. As the frequency increases, the energy increases. Again, the number that makes that relationship true is a constant. You should also memorize this one. It would be Planck's constant at 6.626 times 10 to the negative 34th joules times seconds. You should know this formula and know again that this is the energy of a single photon. So you may need Avogadro's number to convert from 1 photon to a mole of photons, and we'll practice that in the calculations. If you want to derive, if you have room in your head and you want to derive one more formula, you can combine the two that we already know. Speed of light equals wavelength times frequency, and energy equals Planck's constant times frequency, to give you an energy equals speed of light and wavelength formula. So if we solve speed of light for frequency, that would give us, C over wavelength, which then we can take and substitute into this formula for frequency to give us E equals H times C over wavelength. So if you want, you can memorize this formula as well, or you can do your calculations in 2 steps if you're given frequency and asked for energy. So know that for this unit, I need you to memorize these. I think memorizing as you go makes you faster and helps you in the long run. But on the AP formula sheet, if you forget these numbers, they are there for the free response as well as the formulas. So notice what you're given. Notice it's in the atomic structure section of the formula sheet. And you're even given Avogadro's number here in case you forget it for some reason and need it during the exam, you'll have it. Also know that they give you the charge of an electron, but very seldom are there questions that actually ask you to use it. Just kind of try to remember that it's here so that if something shows up asking you the charge of an electron, you remember that you have that as a resource. So let's do calculation, and we'll kind of work this together. Magnetic resonance imaging, or MRIs, is we're all pretty familiar with that as a diagnostic tool, and many of us have had MRIs as part of diagnosis for medical conditions. These usually operate at a pretty high frequency, we think, it looks like it, but it's actually 400 megahertz. So this feels like a high frequency when you don't know what you're talking about, and we'll look at that. So the calculations ask for wavelength and energy, etc. So the first thing I want to do is make sure that this megahertz is in per seconds, but hertz equals per seconds, so I have to convert megahertz to hertz first. So I'm going to do that before we even begin. 4.00 times 10 to the second with 3 sig figs, megahertz, and then megahertz to hertz, and you never would need to show this step, but just remember that 1 hertz is the same as 1 per second. 1 megahertz is 10 to the 6 hertz, so this gives us a frequency of 4.00 times 10 to the 8th per second. And I'm going to go ahead and use this as my frequency in the calculations. So calculation A asks for wavelength, so we're going to take the speed of light, which relates the two, and solve it for wavelength, which would be speed of light over frequency. And I'm going to plug in 2.998 times 10 to the 8th meters per second for wavelength. And I'm going to plug in my frequency that I was given and that I converted, 4 times 10 to the 8th per seconds, which then will divide out to give us almost 3/4 at 0.7495, with 3 sig figs is 0.750. Notice that the seconds cancel, leaving us meters. Okay. So in part B, excuse me, I'm not sure what's going on here. I've been having technological difficulties. This is my third attempt at this video, so hopefully this cooperates. So in my second part of this calculation, we're going to calculate the energy in joules per photon. So this would be E equals, I could use either formula, but since I know the frequency, it's fastest to use H times frequency. So this will be 6.626 times 10 to the negative 34th joules seconds times the frequency, which I converted already to per second. So 4 times 10 to the 8th per seconds. And the seconds cancel, leaving me with joules. And I calculated 2.6504 times 10 to the negative 25th joules per photon, which is actually a pretty small amount, and with three significant figures would be 2.65 times 10 to the negative 25th joules per photon. So you can see how you use that formula. And then they want this in kilojoules per mole. So I'm going to come back and use the expanded version, not the rounded version. Oh, somehow this got cut off up here, sorry. Let me fix this. And that crashed. Okay, so let's come back and look at this. And this would be 2.6504 times 10 to the negative 25th joules per photon. And I'm going to actually rewrite this so that my per photon is in the denominator, so that I can convert this carefully. And this would be photons to moles of photons. So 1 mole is 6.022 times 10 to the 23rd photons, because Avogadro's number works for everything. And then joules to kilojoules, because they asked me to, and I can go from there. So this gives me 1.596, a bunch of numbers, times 10 to the negative 4th. I'm going to round that again to 1.60 times 10 to the negative 4th kilojoules. Notice that the photons cancel, the joules cancel, so this will be kilojoules per mole of photons. So there's my answer to that part. I'm going to use the wavelength to determine the region of the spectrum. So we'll come back up and remind ourselves that our wavelength, which also somehow disappeared, was 0.750 meters. And we'll come down here and look at the spectrum and see that, by the way, that would be 0.750 would equal 7.5 times 10 to the negative 1st meters, which is going to fit somewhere in here. Okay, so this is microwave region according to this spectrum. Just read whatever spectrum you're given really carefully, and remember to check your units for wavelength. We had meters, so this is all okay. One more thing I want to talk about with you, and that would be the emission and absorption spectrum and how they're formed and what happens. And this is actually something that Bohr worked with. So what happens is that most of the transitions from the electron and the hydrogen atom, the one electron in the hydrogen atom, we would picture would be from energy level 7 or 6 or 5 or 4 when they've excited down to the first energy level. But actually there are this many transitions of the electron in the hydrogen atom. And so we can see that, and maybe even more, because we could also go from 7 to 5 or 7 to 6, etc. And each of these, we call them in different series because they're coming down to the same energy level. The only ones that are visible are the ones in the Balmer series. So each one of these transitions corresponds to a different wavelength of an energy of light, right? Something that I want you to think about is that the energy level here is the nucleus, closest, energy level 1 is closest to the nucleus. So the nucleus would be here, and the edge of the atom would be out here somewhere. The way that we worry about this, or the way that we discuss this, is that the edge of the atom gets an energy of 0 kilojoules. And so what's happening as we come closer to the nucleus, these values are negative, right? So this would be the most negative value as we're close to the nucleus. The reason that we do this is because we would have to add that much energy to get the electron to leave the atom, which is what we call ionization energy. So we want that to be, if we can manage to add enough energy from whatever that negative value is to 0, we will be able to force the electron to leave. So remember that as we're talking about ionization energy in the next part of this unit. So the Balmer series has 5 transitions, all from something to the second energy level, and these are the only ones that we can see. So in an emission spectrum for hydrogen, we can actually correlate these lines to each of those transitions. So the one that is the lowest energy has the longest wavelength, which would be this one, transitions to the one with the lowest energy difference change, which would be from 3 to 2. So you can see that this line corresponds to that energy transition. That means the one with the most energy up here corresponds to the transition with the most energy difference from 7 to 2. And they would line up. So this would be from 4 to 2, and this would be from 5 to 2, 6 to 2, etc. Okay, I think this is kind of cool. And we could assign wavelengths based on what we have there. And so someone has done this for us, and I wrote them for you here. Please remember that this would be the amount of energy emitted when the atom returns to ground state. So the emission spectrum comes from the emission when the electron returns to ground state, or the lowest energy state possible. The absorption spectrum would be the exact same amount of energy, hence they line up, right? But this would be how much energy would be required to be absorbed to get the atom to have that electron go to the higher energy state, the excited state. So remember, the absorption spectrum is to excite the atom, and the emission spectrum is to return it to ground state, but the wavelengths would correspond to each other. And I think that that's it for what we need to talk about in this lecture. So I will go ahead and let you look over your learning targets again, make sure that you've added what you need to them, make sure that you come ready to class with questions that you might have, and thank you.